Hello and welcome to a new episode of What's Up with the Universe. I'm your host, Hugh. Okay, we are back from a little break, but today we are talking about how telescopes change our understanding of the universe. Yes, if you are new to this channel, don't forget to hit that little subscribe button and that little bell so you know when I go live. And if you like the stream, hit thumbs up. If you don't, hit thumbs down. Hey, either way, either or. Case around, case around. Well, today's show is about how telescopes changed our understanding of the universe. Yes. 400 years ago, before telescopes, our understanding of the universe was very different. I mean, that is what was believed. We lived in a spherical ball orbited by the rest of a finite spherical universe. Earth does not move. It is the center of the universe. Our sun orbits the Earth, as do all other planets and the moon. The stars are distant objects, however perfect and unchanging. I mean, how do telescopes associated technology unlock the secrets of the universe and help us towards the understanding we have today where Earth is no longer at the center of the universe? I mean, instead, we know that ours is a small planet orbiting a star in the suburbs of a large galaxy, filled with billions of other galaxies becoming increasingly ever distant from each other by the expansion of space. This is the story of how telescopes continuously changed our understanding of the universe and our place in it, transforming our own view of the universe. Of course, we still have much more to discover. Before telescopes, we could only use our eyes and a variety of measuring instruments to plot positions of the stars and the planets, and the positions and movements of objects in the sky to create a limited understanding of our own universe. We had no way to know what these actual objects were and little evidence for our relationship to the cosmos. A fascinating fact is the position accuracy of any object in the sky before telescopes was about 1 arc minute or 1/60th of a degree, the limited resolution of the human eye. Yet some amazing things were discovered by pre-telescope astronomers, such as the distance to the moon and the relative separations of the sun and the planets, and of course the elliptical orbits of planets itself. I mean, over the years, we had many questions about our universe. Of course, there's some big questions about whose answers were relieved by increasingly sophisticated telescopes and telescope technologies that helped us reassess our own place in the universe. We're going to ask different questions. The first question, is Earth or the Sun at the center? Which one is which? I mean, before telescopes, there was no evidence that Earth orbited the Sun, and not the other way around. Prior to about 400 degrees ago, it was generally believed that Earth was at the center of the universe, as in Aristotle's model. And everything else, the sun, the moon, the planets, the stars, it all revolved around it. A competing theory advanced by Copernicus in the early 1500s was that the sun was at the center of the Earth, was at the center and the Earth orbited it. It would take a telescope to determine which one was true. Of course, in 310, between 310 and 230 BC lived Aristarchus. He proposed that a sun-centered system based on his calculation that the sun was the biggest object in the cosmos. But of course, his work was ignored for 1500 years. I mean, both Aristotle and Copernicus' models have shown that on the side should have eclipses. These have been eliminated here for specifically, Aristotle and Ptolemy needed them mostly to account for the retrograde motion, and Copernicus needed them because he insisted on making the planet's orbits exactly circular. Eclipses were the needed way to explain the deviations of the planet's motions from that of the circles itself. I mean, when Galileo came along, he decided to do some observations of his own. After hearing of this new invention called a spyglass, Galileo made a small telescope with a lens and turned it toward the sky. I mean, Galileo, he reported evidence that the Earth was not the center of the known universe, but the sun itself held the central position with the Earth orbiting around it. The most compelling evidence he found was that the phases of Venus. As you can see in this illustration here, these are from the perspective of Earth itself. They show how the phases of Venus will look in the Earth-centered system compared to that of the Sun-centered system. Note that the Earth-centered system, Venus will look like a crescent. It would never get any larger than a crescent. Let me a little bigger thing for you here. Okay, gotcha. Actually, better now. The lit portion of Venus would wax and wane more like the moon. Sometimes Venus would look like a crescent. But at times during its orbit, Venus would become almost full. Which one do you suppose Galileo observed? Well, Venus phases that would be produced by a sun-centered system, a small telescope provided compelling evidence that our sun was at the center of our solar system, not the Earth. Our understanding of the universe was forever changed. And by the way, Galileo did not invent the telescope. Credit for his invention is now seems to go to, let me see if I can pronounce his name correctly here, Zacharias Janssen in December of 1608. Of course, Galileo's skills at making lenses and his insight of what to look at turned the curiosity into a research instrument. The second question we're going to ask, how far away are the stars? I mean, as previously mentioned, shortly before the telescope was invented, two competing theories of the structure of the universe was debated. The long-held structure of Aristotle with the Earth at the center, and the newer theory of Copernicus that the sun was at the center. I mean, one of these arguments against Copernicus' notion that the Earth orbited the sun was that we could see no change in the position of the stars over the course of the year. Let's see what this means, okay? This is how star positions would appear to change over 6 months' time, from one side of Earth's orbit to the other. If the stars are about 5,000 times closer to us than they really are, the arrow marks one of the sides right here. About 10 years, you can tell away. You can tell which stars are closer and which are farther apart by the star's parallax. But how far are the stars really? Okay, pretend that the sun is the bridge of your nose, and the Earth orbits over your face. Your eyes at either side of the Earth's orbit. Now, hold your finger in front of your arm's length. Imagine a star perched on the tip of your finger. When the Earth is on the side of its orbit, point to one eye. Close the other eye. Now notice, where the tip of your finger is against the background stars. Now the Earth is on the other side of its orbit. Point the other eye. See how much the tip of your finger appears to move across the stars? Okay, now let's move you and your face representing Earth's orbit to the correct distance from the star on your finger. Now, if you have the star on the tip of your finger, hold your finger up, you need to move about 15 miles away, then close one eye to the other. That's the amount of parallax, or apparent change of position. The star Epsilon Eridon really has. I mean, no wonder the tiny change couldn't be seen without a telescope. But if parallax could be measured, a simple formula could be applied to determine the distance of the star. I mean, many astronomers were studying the problem. While pinpointing positions of 50,000 stars using instruments at the Konigsburg Observatory, Frederick Wilhelm Bessel was the first, in 1838, to measure the parallax of a nearby star, setting an accurate distance scale for the stars. We can now know the stars are tremendously far away. The nearest visible star is about 4 light years away. That's about over 20 trillion miles. I didn't want to do the exact calculations for you because there's a lot of zeros. In 1800s, there was no one guessing the stars were that far away. This diagram here at the bottom of the slide, it represents the Earth is in orbit around the Sun, showing its position now and 6 months from now. The apparent location of the closest star changes relative to the background stars. The third question, what are stars made of? Well, in 1835, the French philosopher Auguste Comte, can't pronounce his last name, stated, quote, that humanity would never be able to determine the chemical composition of the stars, unquote. Of course, the seeds of discovery has already been sown. In 1814, Joseph Fraunhofer used an instrument at the same observatory. It was called a heliometer to study the spectrum of the sun. What is a spectrum basically? The rainbow is the white light from the sun spread out to the colors it is made from. If we could take a section of the rainbow and basically magnify it so it was a few feet wide, we would see the dark lines in the rainbow just like Fraunhofer. This expanded rainbow is called a spectrum. Of course, many people ask, like, so what do these dark lines mean, right? Well, those dark lines turn out to be the fingerprints of the elements that made up the atoms of the sun's atmosphere itself. This way, we can determine what it was made of. In 1859, two German chemists named Kirchhoff and Bunsen, Robert Bunsen of the Bunsen burner fame, yes, he discovered that the dark lines in Fraunhofer's spectrum matched exactly lines seen in the spectrum of gas flames in their laboratory. They discovered the elements like iron, magnesium, copper, zinc, and nickel in a solar spectrum. I mean, what elements can you find in this simulated solar spectrum? We can match exactly the 3 lines in the spectrum of the hydrogen. I mean, to the 3 lines of the solar spectrum: hydrogen, helium, and sodium. Of course, but the calcium and water lines show up in the spectrum of the sun's atmosphere. By 1863, the spectra of stars revealed these same dark lines, characteristic fingerprints of known elements. All these elements were the same kind of elements found in the sun, our very own sun. It had been supposed for many years that the stars were other suns, but this actually confirmed that the sun is a star, just one that is very close to us. So this confirms the stars are other suns. If you want to read more about this, you can check out William Huggins, because in 1863 he was one of the first to publish results of his spectral analysis of stars. Question 4. Should I get a drink of water? No, I'm going to get a drink of soda. One moment. Okay, question 4.1. Where is the location of the sun in the galaxy? Well, it was about less than 100 years ago, with no evidence, To the contrary, it was still widely held that the Sun, along with its planets, was at the center of the known universe. It was still unknown that a galaxy was just one of billions. Many astronomers still thought, with no other evidence available, that our galaxy was the only universe. But could the solar system's location on a galaxy or the known universe actually be determined? Well, in 1914, the largest telescope in the world at the time had recently been constructed at Mount Wilson in Southern California. It was it still is, a 60-inch reflector. Harlow Shapley, originally a journalist, now turned astronomer, he began observing globular clusters, these compact spheres of thousands of stars, through a 60-inch telescope. At Harvard in 1918, Henrietta Leavitt and Harlow Shapley developed an accurate method of measuring large distances by using a particular type of star called a cephalid variable. Shapley discovered cephalid variable stars in many of the clusters. Using this, Shapley was able to estimate the distance to the clusters. Of course, how cephalid variables are used to measure distances. They are variable stars with regular periods. The length of a cephaloid's period is directly proportional to its absolute luminosity. So, based on the period, we can calculate how bright the star should be, and we can see how dim it appears to be. So we can calculate then how far away the star must appear to be that dim. If we were at the center of the galaxy, these star clusters should be randomly distributed in all directions all around us. Using the distance to the star clusters, Shapley mapped the three-dimensional distribution of these star clusters. And what did this mapping actually reveal? Well, in 1918, Shapley published a report that the clusters were found to be in a spherical distribution in one direction toward the constellation Sagittarius. The location of the center of our own galaxy has been determined, and we weren't there. Yeah, in fact, the solar system and the sun and the planets was so far away from the center, out in the suburbs, way out in the suburbs. Our place in the universe had once again changed. Another question that just came up was, is it one galaxy or many? Of course, as I mentioned before, less than 100 years ago, it was still unknown whether a galaxy was the whole universe or just one of many galaxies. Spiral nebulae, quote-unquote spiral nebulae, have been observed and studied since the early 19th centuries. The term nebulae refers to their fuzzy or gaseous appearances. This was the variety in the structures or shape that could be documented, but their size was unknown because their distance was unknown as well. But that all changed in 1824 thanks to Edwin Hubble. He used the telescope at Mount Wilson's 100-inch telescope, the newly built one. He looked for cephaloid variables at the same time using stars by Shapley. In the Andromeda Nebula, I call it a nebula because this is what they called it at the time. Finally, there was a telescope with resolution and light gathering power to see individual stars of one of these nebulae. Hubble compared how bright these stars were and how they looked in Andromeda to how bright they looked in our own Milky Way galaxy. He could estimate the distance to them and the nebula. The huge distance measured about 2 million light years away. That means Andromeda itself was huge and a galaxy in its own right individual. I mean, suddenly, our universe was not just the Milky Way. It was filled with a cosmos of galaxies. I mean, this is the ultra-deep Hubble field. If you want to know exactly how much of the sky this picture is, hold your arm at arm's length, put your thumb up, and the shape of your thumbnail is the size of the image they took. That's a very small patch of sky. Our universe is large. And after this, another question came up among scientists. Did the universe actually have a beginning? Well, in 1929, Edwin Hubble made another universe-shocking discovery. The universe is expanding. Yes, Mr. Hubble observed that the more distant galaxies are receding faster than closer galaxies. This caused a number of scientists to hypothesize that the universe had expanded from a state of extremely high density and temperature billions of years ago and has been expanding ever since. I mean, the initial state was mostly extremely high energy radiation, which, as the universe expanded and cooled, was mostly converted to matter. Any leftover radiation would have been stretched to lower energies as the universe expanded, looking like radiation from something with a temperature just a few degrees above absolute zero. I mean, if this quote-unquote leftover radiation was detected, it would support the hypotheses of the Big Bang origin of the universe. No, Miss Miles, direction does not matter. The evidence of Big Bang was detected in 1965 in the form of the cosmic microwave background radiation. This provided the evidence. Arnold Penzias, how's his name? Sheesh, and Robert Wilson in 1963. They were studying the sky's microwave background, quote-unquote, noise like radio static for Bell Telephone's laboratories using a huge radio telescope. They did not know what they got at first, and they thought they were catching pigeon droppings. So both of them cleaned up the telescope and tried again. They got the same noise. They realized they had detected microwaves coming from all around the sky, a universal background radiation. Robert Drake, a physicist nearby at Princeton University, he learned of the measurement and in 1965 correctly interpreted it as radiation of about 3 degrees above absolute zero, the predicted radiation left over from the Big Bang. I mean, if you want to hear it yourself, turn in a radio station or a TV station if you still got static, and on the radio, between the stations, you can hear a small amount of static or a hiss. That is what you hear. That is noise caused by the cosmic radiation background itself. That little hiss. I mean, since Edwin Hubble discovered distant galaxies were receding, and we discovered evidence of the Big Bang, it was suggested that we could determine how long ago the Big Bang occurred by figuring out the expansion rate of the universe and calculating out the expansion rate of the universe and calculating back to the beginning itself. Additionally, observations, we decided to use the Hubble Space Telescope, named after Edwin Hubble himself. The data, and of course data from the Wilkinson's Microwave Astronomy Project, the WMAP, they both have pinpointed the time of the Big Bang as about 13.7 billion years ago, or give or take 1% or 100 million years or so. I mean, this image here, tiny fractions of a second. This is pretty cool. I love this little image right here. 338,000 years ago, the image of the universe is related by Wilkinson's microwave by the WMAP. It was basically tiny millionth of a degree temperature fluctuations with an extraordinarily evenly dispersed microwave light. I can't talk. It was basically at 2.73 degrees above absolute zero. The entire sky glows with a brightness that was astonishingly uniform in every direction. I mean, WMAP, it can see the tiny ripples or seas that was expected from the Big Bang, and which generated the cosmic structure seen today. So 13.7 billion years ago, the image Hubble of our universe as we view it today. One of the last questions we have, are there any other worlds? Well, within our galaxy and other galaxies, there are other worlds like those in our solar system. I mean, before telescopes, we only knew of 6 planets around the Sun: Mercury, Venus, Earth, Mars, and Jupiter. The first new world ever discovered was by William Herschel, who built the largest telescope at the time, was a 1.2 meter reflector. It's about 49 inches long. The larger, more powerful telescope enabled Herschel to probe deeper into space. In 1781, he discovered a new planet called Uranus. Not Uranus, Uranus. It orbits the Sun far beyond the Saturn, of course. Many people ask, but what about other stars beyond the solar system and other stars? Well, scientists first started to find planets around other stars in our own galaxy in the 1990s. So far, we've discovered over 4,000 exoplanets around these stars. I mean, many of these exoplanets we know were discovered with the Keck telescope in Hawaii by Geoff Marcy and Paul Butler. All of a sudden, our solar system basically no longer unique. We're not individuals anymore. We're part of potentially millions of other stars that also have planetary systems and possible life. Our understanding of our place in the universe had changed. I mean, once again, the universe provided to be even a more amazing place than we ever imagined. So, as the telescope and telescope technologies became more sophisticated, so has our understanding of the universe. I mean, answering some of these big questions, some of the answers we discovered, telescopes and technologies have brought us from Earth and being the center of the universe to revealing that ours is just a small planet orbiting a star in the suburbs of a large galaxy, filled with billions of other stars and planets, surrounded by billions of other galaxies, becoming increasingly ever distant from each other by the accelerating expansion of space. And still, we have more to learn. I mean, how did galaxies start forming in the first place? Will we ever find evidence of life in planets outside of our own solar system? I mean, what else will we know? I mean, the more we discover as we build larger and more sensitive telescopes, there's still universal possibilities. Of course, that's why I always ask, what's up with the universe? We've got the James Webb Telescope launching pretty soon. I want to thank everybody for tuning in today. Well, we talked about telescopes and some of the discoveries they have talked about, and hopefully I did not get too technical for you. So if you do not subscribe and you want to find out when I go live, don't forget to ring that bell. If you like the show, hit thumbs up. If you don't, hit thumbs down. Either or, hey, it's science. Your preference. So thank you, everybody, and have a good night.